Okay, so the next part here we're looking at is something called a molar mass. So what a molar mass is basically talking about the mass of 1 mole. So for example, let's forget about moles for a second and let's say, well, how much does 1 dozen weigh? Well, it depends on what the dozen is of. So for example, if I have 1 dozen elephants, that's going to weigh very differently than 1 dozen feathers. They're both the same number, 12 elephants and 12 feathers, but they don't have the same mass. What about if I had a dozen people or a dozen pencils, right? A dozen cookies versus a dozen chairs. Every single type of thing has a different mass. And that's no different when you're looking at atoms or molecules or any particles. A dozen of anything has different numbers. For mass, same thing here. If I have 1 mole of elephants versus 1 mole of feathers, it's exactly the same thing. 6.02 times 10 to the 23 elephants is going to weigh very differently than 6.02 times 10 to the 23 feathers, right? Just make sure you remember the number is associated with the word mole. Okay? Well, when you're looking at the periodic table, we can actually get information about the mass of elements, right? We know that from the periodic table, we have the atomic mass. So, for example, let me just quickly show you on ptable.com. Right, I'm going to shift this over. Right, so here, oh boy. I just hit my link, we went to our Learning Commons library. Okay, so this number that's here, right, so this weight, 1.008 for hydrogen, remember that's the average atomic mass. So all of those masses that are on here give us information about the weight of an atom. Well, we can use that for when we're trying to determine the molar mass. And actually, the molar mass is equivalent to the mass of the atom. But just like everything else, the masses of atoms are going to be different. If I compare aluminum to magnesium, they're going to have different atomic masses. So 1 aluminum atom is approximately 26.93 atomic mass units, right? The symbol is a little u. We've seen this already when we looked at average atomic mass. 1 magnesium is 24.31 atomic mass units. They weigh differently. If I compare that to hydrogen, hydrogen was 1.001 approximately, much lighter than any of those other two. So every element on the periodic table has its own unique mass. So that mass on the periodic table is now going to be referred to as our molar mass. So what does that mean? Like, what does that value represent? So if you were to take 1 mole of those atoms, the mass in grams would be equal to what the mass would be on the periodic table. So 1 mole of aluminum atoms would now weigh 26.98 grams. 1 mole of magnesium atoms has a mass of 24.31 grams. If we were to look at 1 mole of hydrogen, it would weigh 1.01 grams. So this just translates for us, if you were to weigh it on a scale, like let's say I had aluminum foil, okay? And I want to check out how big is 1 mole using aluminum foil? Well, I'd have to take out my scale and weigh out 26.98 grams. And what you would be looking at is probably a square, not too big, don't try this at home. Don't waste your aluminum foil at home. But it would not be a big square. Maybe enough to, let's say you're wrapping up a sandwich. Okay, it's not a huge piece of aluminum foil that would be equal to 1 mole. So in that sheet of foil, you have 6.02 times 10 to the 23 atoms. That's what that means. We now have a mass measurement for those particles. So now the number on the periodic table can go two ways. We can interpret it as the molar mass, and the unit is grams per mole. Or it can still, of course, what we've been learning up till now is that it's the atomic mass. It's the exact same number. The only difference is the units we're using. So let's go to hydrogen again. So hydrogen's molar mass is 1.01 grams per mole. Or we can say hydrogen's atomic mass is 1.01 atomic mass units. It's exactly the same thing. It's just that you didn't know about this before, and now you know. So let's talk about, well, what happens if you have a molecule? So there we were looking at like atoms, right? So aluminum, magnesium, hydrogen. But what happens if you have something with multiples? Like I have a NH3 or H2O or anything that has more than one element in it. Well, how you can figure out the mass is you basically add up all of the individual atoms that are part of it. So let's say we wanted to know the mass of NH3 for one molecule. Okay, well, I would add up nitrogen and 3 times hydrogen to give me a total mass. Molar mass is the same way. If I want to know how much 1 mole of ammonia is, NH3, I would take the mass of nitrogen and 3 times the mass of hydrogen to give me the total mass. So what that means is if I had ammonia and I wanted 1 mole of ammonia, I would have to weigh out 17.04 grams. So let's do another one. Let's say water. Okay, I'm going to show you the setup of how to do this, how I would like you to do these questions. So when you're determining the molar mass, what I would like you to do is show what are the atoms you are adding up. So 2 times hydrogen and 1 times oxygen, right? So we're adding that up. I don't know why I have this guy here. I don't need this. Okay, so you must show me the multiplication you're doing and what you're adding together. So the numbers here are going to be the numbers from the periodic table. Now, when I am doing molar mass, I always round to 2 decimal places. Okay, so technically molar mass doesn't really have significant digits, but I'm going to explain to you why I round it to 2 decimals. So most of the molar masses you're going to see, it could have 3 or 4 decimal places, right? Some have 4 and some have 3. Later on, as we learn more in this unit, we're going to start using these numbers for more calculations. So what I find is if you round it too much, so let's say magnesium, if I were to round this to the number 24, I find that it gets too rounded and it will impact your final answer in like when we're doing more calculations using that number. However, if you keep all your numbers, so let's say we kept all 3 decimal places, it doesn't really have an impact on the number that it would have otherwise. So I find 2 decimal places is the sweet spot. I would say 2 decimal places is the minimum you have to do. You can keep the entire number if you'd like, but you cannot round this to a whole number. Okay, so any handout, answer key, anything you look at mine, you're going to see I use 2 decimal places. So hydrogen is 1.01 after it's been rounded. So over here I have 1.01. And remember the units are grams per mole now because we're doing the molar mass. So this is the molar mass of hydrogen water. And then for oxygen, we're going to have 1 oxygen. So oxygen's molar mass, this would round to 16.00. So over here, we would have 16.00 grams per mole. And then we're going to work this through. So you're going to have 2 times 1.01 plus 1 times 16. So we get 18.02 grams per mole. So what does this mean? It means in 1 mole of water, right, 1 mole of water would weigh 18.02 grams. So on a scale, if you were to weigh out 18.02 grams, that means that we have 6.02 times 10 to the 23 water particles there. So the molar mass just kind of lets us figure out, well, how much would these things weigh? Because we can't count them out. We don't even have the capability of doing that, right? Because they're so small. But we can determine the mass of it and then weigh out large quantities of this. And you would do the same thing for any structure, like say, let's say sugar. If I want the molar mass of sugar, I would do 6 times carbon, 12 times hydrogen, and 6 times oxygen, and add that all up. And that would give me the molar mass of sugar. You can figure out the molar mass of any molecule, of any ionic compound. As long as if you have a periodic table, you can figure out the molar mass. So from now on, we're pretty much always going to use the unit for molar mass as being grams per mole. So this is written out the full way, but you can use grams per mole, and this is what you're going to see me use. Okay? So here's another example. So here's carbon dioxide. If we wanted to figure out the molar mass for carbon dioxide, right, we have 1 carbon plus 2 oxygens. So how you can write this out for me, I find it's the easiest, is this. Okay, and then you give me my answer. But you have to, I need to see what atoms, how many of each atom are you adding up? Because I'll tell you now, later on, we're going to build on this. This unit, everything builds on each other. So if your molar mass is incorrect, later on, the other calculations you're going to do are going to be incorrect. So it's very important that you're adding and you have the correct number for each element. Okay, so that means 1 mole is 44.01 grams. All right. So when you're looking at a formula, let's say for ammonia, NH3, we can now talk about this as being a molecule of ammonia, or we can say that this is a mole of ammonia. Okay, so what do I mean by that? So let's say we have 1 NH3, like 1 molecule. To make this, we need 1 nitrogen atom and 3 hydrogen atoms, right? NH3. But let's say we had 1 mole worth of NH3. 1 mole worth. In order to make this, we would need 1 mole of nitrogen and 3 moles of hydrogen. So remember, these are just numbers. Think of this as an assembly line. I need to make 1 mole worth of NH3. Okay, well, to make that, for every 1 I'm making, I need 1 nitrogen and I need 3 hydrogens. So the ratio is 1 to 3. Okay, I'm going to give you a different example, like a different analogy here. Let's say we wanted to, we're going to build some bikes. Obviously, this is like an amazing, fantastic bike. But to make a bike, we need the bike frame, let's say, and we need 2 wheels, right? To make 1 bike. So 1 frame plus 2 wheels equals 1 bike. Okay, so these are essentially ratios. I need 1 frame for every 2 wheels. What if I wanted to make 10 bikes? let's continue in the next part.